has published some follow-up observations of near-Earth objects, and if you wanted to go find his paper on that, you can go onto the NASA ADS website. And Connor has been doing work with exoplanets. His observations helped confirm a hot Jupiter. And both of them were working with data from this telescope. So, yeah, lots of fun. Any questions right off? Or should I just go in my spiel? Spiel, okay. So this is the 2-meter Faulkes Telescope North. And when we talk about the size of a telescope, we talk about the diameter of the primary mirror, which is right here. The Faulkes Telescope was built by the Dill Faulkes Foundation in 2001. The idea of the Faulkes Telescope was, now, why would anyone want to have a telescope halfway around the world that you could control over the internet?
Look at stars at night during the day.
So you can look at stars during the day, exactly. Okay? This telescope was built primarily for kids in England, in particular public schools. Dill Faulkes, he went to the public schools and did very well for himself, but he saw a lot of the time the private schools seemed to always have these wonderful things, these wonderful trips, and so he wanted to give back to the public school system in England by providing a telescope that they could use during school hours. And so he built this one, also the telescope in Siding Springs, Australia. And both of those telescopes were purchased by Los Cumbres Observatory Global Telescope Network. That's a privately held, non-profit organization, so not a penny of tax dollars goes into this telescope. It's all private donations, privately funded. And the idea of this, of having a telescope halfway around the world so that you could use it real time during your daytime, seemed like a really neat idea to some of the beginning people in Los Cumbres. And they said, well, hey, what about this? Let's build a network of telescopes worldwide. We're going to deploy a bunch of something like 12 to 15 1 meters and 24 0.4 meters. Okay, so 0.4 meters are about this big around and sort of, you know, this tall, but still usable for good student science, and a lot of pretty pictures, a lot of fun learning how to use the telescopes to begin with. And then the 1 meters, those are capable of professional grade science. Okay, but of course, anything that shows up here, I'm going to make sure the kids get a cut of the time. The time on this telescope, the lease with the university, is that the university gets 30% of the nighttime, and that is explicitly for education and outreach. So any kids that want to use the telescope can really help out a professional astronomer by working with them, because then the professional astronomer can get observing time. And the student can do real research, and you've learned a lot from doing this, haven't you? You've learned a lot from doing this, haven't you? Yeah. So it's a really good situation where we can work with the kids, the schools. The type of research that's being done on this. Who has a favorite area of astronomical research?
Gravitational lensing.
Gravitational lensing. Okay, not too much has been done with that, but some exoplanet work has. So there are 13 exoplanets. And these exoplanets are planets that orbit stars other than our own sun. Okay? There are 13 planets, exoplanets, that have been detected using gravitational lensing, and this telescope right here helped do that. That one was the hard one. I was also working with some students at Maui High School, and we were considering looking at a double-lensed gravitationally lensed quasar to see if we could measure the phase time. In other words, as the two paths, there's a big mass here, the light takes two paths and comes to us, and it looks like it's in two positions on the sky. Those two paths effectively have a different length for the light. And so you can actually, as the quasar varies, in principle, you can measure the difference in path length. But it had already been done. I was really disappointed. So he's doing something else with quasars. That student is doing something else with quasars. Yeah.
So does this dome open? I mean, how does it get to the sky?
Yeah, so this entire dome folds back down.
Okay. And what hours is it?
It'll open up shortly after sunset. And like I was telling you outside, this is a fully robotic telescope. We usually keep an eye on it, but if everything's working right, it'll wake itself up, it'll do some calibration measurements, open the dome if the sky is clear, if the weather's good, and start doing observations. If it's supposed to be doing real-time interface observations, then it'll wait for the user to give a command when the time comes. Or if it's doing queued observations, it'll take the queue observations, all the observations from the queue, sort out which ones it's supposed to do, which ones are highest priority, and it'll automatically make decisions in order to get the observations done.
And then where does all the data go?
The data shows up on, so for the real-time interface, it's available immediately on the web. Even to anybody, even if you're not logged in and controlling the telescope, even if you're not logged in and don't have an account with Las Cumbres Observatories, you can go to their site and look at the last image taken with the telescope in real time. The queue time has a proprietary period to allow researchers to get their papers out before somebody else scoops them with their own data. But the real-time interface data, you can go on and click on and see what the last image was. There's a whole archive. You can go through years of data.
How do we get these websites?
Well, what you can do is you can go to Las Cumbres Observatory.
Follow you around.
Yeah, exactly. If you'll ask Becky, I will give her a direct link so you can, instead of searching around the website, you can just go, boom, I want to go do this. Okay? Yeah.
Just wondering, what's the yellow stuff? How is this?
All right, I'll get back to that. It's just insulation. But, so the queue time data does go on an archive server, and then whoever programmed the observations in, they're probably asleep when it's happening. At least I try to be. And then they get an email the next day as soon as the data's ready. And trust me, this is so much nicer for astronomers. About the third or fourth time you go up to Mauna Kea to observe on the 88-inch telescope, you're done. You're ready to use this system, I'll tell you.
Really?
Yeah. So the foam in the ceiling up here, that's just spray-on foam. That was put up there for insulation. You feel that it's a little bit colder inside than outside? Should be a little bit. If we were to go into pan start, they keep it cold in there. I mean cold. But by putting the spray foam up there, we can keep the temperature in here almost the temperature of when we're opening up at night without any problem. Now, why would we want to have the temperature of the telescope be the same temperature as outside when we open up at night?
Just so it doesn't like things up, I guess.
Yeah. Right. So exactly. Well, so it kind of settles in and is ready. That's actually probably not a bad idea, Mark. Would you say that having the temperature be already at the same temperature that it's going to be observing at is a good idea, so that you don't go through some thermal change and have it freeze up or something?
Yeah, not so much freeze up, because if there was conditions where there was actually possible freezing, the enclosure wouldn't open anyway.
Yeah.
So, but that's pretty close because
You get foggy here.
the telescope is a lot. There's about 35 tonne of steel here. So if that's about, let's say, 10 degrees difference to what the ambient temperature is outside, what happens to the telescope at night time? It's off heat, doesn't it? Yeah. What happens then? What about your optics?
What?
What about your optics? The telescope's giving off heat.
Okay, so
Would you want
Why do
to?
stars twinkle?
Yeah. I mean, think about it. You've seen heat rise off the road. As I was driving up, I was noticing the heat rising off the road. Would you want your images of asteroids to be taken through that heat? No. You want the clearest image possible so you can see faint asteroids, because if you spin it around too much, you start losing it in sky brightness. And you also want to have clear images so you can get precise positions, right? So, yeah.
Whenever the binoculars moved a little bit, why was it moving?
So I was moving.
Okay, I was wondering, okay, because that moves when it's open, right?
It does the same thing. It checks out the web page and says, all right, the enclosure's open, and then it just goes into its own routine. It's automated too. So that one and the other two over in this corner here, they do a similar sort of thing. They're doing sky surveys. So
The binoculars raise maximum.
yeah.
I should.
In effect, that's all they are. They are binoculars actually, because they're 18 degrees field of view.
What's that thing?
I moved them before. I just parked the telescopes.
They really work astronomical
They really work when the dome's open. They do some daytime calibrations on the cameras and everything else, and when everything's closed up. That's about
Astronomy all day.
same as this. They're actually mapping the sky. It's doing a similar function to pan-stars, only they haven't got as big a field of view or as powerful a camera. Looking for different
Any night
objects.
the sky is clear, we probably can observe. So it's what, about 78% clear time?
A bit more than that, actually.
A bit more than that?
In the early 80s.
Yeah, and then I was looking about a year ago. I was looking at the statistics for this telescope, and it was on sky about 97% of planned time. And so there are a couple of days around full moon that sometimes we'll plan to take the telescope off sky for engineering. The full moon period, it's you can't see, it really affects astronomy.
Nowadays, of course, the telescope's so good, there is a lot of science to be done during the full moon.
Yeah.
Unfortunately, people tend to take it off sky just out of habit. Because they were allowed to.
Yeah.
How long did it take to do this?
I think it was about 2 years on site, Mark.
About 18 months, something like that. But that's just to actually put it up, build
Yeah.
the enclosure.
Don't worry. That's a happy sound to
It's
me.
just waking up.
Was waking up? Good.
I just wake it up.
Oh, it's moving.
Oh, look, it's what? Oh, what's it doing?
It's actually just timing the encoders at the moment.
No, the kids. Oh. There you go.
If you go on how long it actually takes to
Well,
build
take a
one,
picture.
the design and everything else, you're probably talking about anything from 5 to 7 years. The company that actually built this telescope were pretty good actually. They managed to build 5 of these in 5 years, deploy them, and get them operational.
What country?
England. A company called Telescope Technology.
England built the whole
Send me
thing.
that picture. I want to put you on the blog.
Well, parts of
Hey,
it
how are you?
various other places, but the
Rotating.
enclosure was built in Scotland and the telescope was built in Liverpool.
Just to come here. Just for Haleakala. What was it? Or the 5 of them were there.
5 of them were built at the same location. There's the Liverpool Telescope on the Canary Islands. There's one at Coonabarabra in Australia. There's one in China. There's one in Nepal in India. How many's that? 4? I'm missing one somewhere. Yeah.
All right. So, this is Josh, everyone.
Hi, Josh.
So, are you a scientist? Have you been working on astronomy?
Sometimes, yeah.
You want to use this telescope sometime? Okay. There are 2 people here that can really tell you how to get some time to do some science with it. Anthony is published. He actually has a little paper out on